month, we are always at Ruparel College in Matunga. And if a month has a fifth Sunday, we are at Alexandra School in Fort. And the best way to find out about what is happening is to check out the announcements on our Facebook page. And normally we announce the next 2 or 3 ahead of time. If you've checked our Facebook page, you will find that there's nothing announced for the next few sessions. But don't worry, in the last 10 years we've not missed a session. We will not miss it. I wasn't here for a while, so we've not been able to get sessions going. But we are certainly sure of our next session, which is going to be a very interesting one. It is called Science from a Local Train Window. Now, you know that the local trains are the lifeline of the city, and hopefully all of you have traveled by local trains and have looked out of the window, looked inside the compartment, looked at the trains passing by and the wires and everything else. There's a lot of beautiful science that one can see just by traveling by train. And I'm sure there are lots of questions that, maybe while coming here you wondered, why was there a mega block on a Sunday? Why are mega blocks only on the fast lines? Generally there are lots of things you can ask about train journeys, including calculating the speed from just hearing the thud of your train. So it should be a fun session at Ruparel next 2 weeks from now. After that at Prithvi, it should be up by tomorrow, don't worry. We will fix it up because we need to get the posters and everything sent here as well. But there will be a session the first Sunday of the month over here. If not anything, I'll do something, so it's always there. Just remember, the best way to find out about Chai and Y is follow us on Facebook at Chai and Y or Twitter at Chai and Y, and you can ask questions there and post your comments and all that. Okay, with that, it's time to get started with today's session, and it's a pleasure to introduce Vidita. Vidita, where is your presentation?
I'll open.
So Vidita is this is her, I think, third Chai and Y. She is one of our very good outreach, very strongly believes in outreach. And I think Vidita is a neurobiologist at the IFR. She is a Mumbaiker from the suburbs over here, knows this area very well, Xavier's College, Yale University PhD, did postdocs in Sweden, Oxford, etc., and came back and set up a lab at the IFR to study neurobiology. And one of the molecules that she's been working with for the last several years is the central hero of the story today, and that's what she'll tell you about. So over to you, Vidita.
Right there, my youngest audience member. Don't eat it now. Difficult, I know, very difficult, but hold, just hold it, okay? For a little longer. Yeah. I know, it was immediate, right? That's the reaction that usually provokes. That's also controlled by your brain, by the way, interestingly, that reaction. So what I'm going to do today is tell you about the happy chemical, and we'll talk about why it might even ever have been considered the happy chemical. The molecule that is the hero or the heroine of the story is serotonin. It's also known as, we shall forget this name in 2 minutes, 5-hydroxytryptamine, doesn't matter, it's serotonin. We'll also call it the happy chemical. This tiny little molecule, okay? Now you're going to look at the person who's sitting next to you and introduce yourself. As you do so, you're making a social contact. Your brain is dumping out a little bit of serotonin as you do this. So please say hi to the person who's sitting next to you, not someone you came with, ideally. It would have been nice if I could have mixed you up. But even if you came with someone, just say hi to them in any case. You normally don't. And you're going to play a word association test. How many of you have done word association tests? Anybody done word association tests? So what the game is like is if I have a volunteer here and I say to you, Hrithik Roshan, throw a word back to me that comes to you immediately. Doom 2, extra thumb, anything else? So we go back and forth, okay? You say a word and I'll start it off. I will get the ball rolling. It's going to be the same word for everyone. And then you're going to do a word association. If you have a little piece of paper, scribble it down. Those of you who don't have paper, you will most likely have a phone. So scribble it on your phone notes section. Between the two of you, the pair of two, you're going to come up with 5 words for me, okay? And I'm going to get the ball rolling. This is to be fast. Please don't think very hard about what the association is. It's a rapid, quick association test. The word that I'm going to send in your direction is quite obvious. So Have you introduced yourself and made yourself into pairs? Okay, you know who the pair is that you're working with? She doesn't have a partner, walk over. Yeah, so everyone has a dyad, as it would be called in an experiment. Yeah, you're a part of a unit of 2 and you're going to do this word association test. All right. Let's go. Let's start. The word I'm throwing out to each of you, one of the dyad will start in response to each other. Record it for yourself and do it at a slightly softer volume because otherwise everyone is going to be coming up with exactly the same words. Here we go, serotonin. Okay, stop. You should have done 5 words by now. Yes? No? Okay, 1 more minute. Come on, go fast. Rapid association. Don't worry about it making sense. It's just an association. Okay, stop. Whatever you have, even if it's 2 words, 3 words, wherever you got to, just stop, okay? I bet since 2 seconds ago I flashed some words up there, some of those were in your list because they're right at the top of your working memory, obviously, right? Just 2 seconds I gave you word associations. They're the first words that are going to come out, right? So some of you may have thought happiness. How many thought happiness? Yeah, so many of you would have thought happiness because I just said happy like 5 times before that. So it's likely it's in your RAM. You'll have, some of you may have brain in there. How many have brain in there? Okay, good. So there's a lot of people thinking this thing is floating around in the brain. All right, so now we're going to look at some of these words and you all are going to count them off that you all have in your own list. And then I'm going to look to see what else threw up from here, okay? And this is just me doing this association task. It's my biased list, okay? So, yeah, we have brain, happiness, antidepressant, anyone? Yeah, depression, anxiety, learning, sleep. Anyone with sleep? Very good, interesting, okay? Sleep, mood, okay. Expected suicide, anyone? Okay. All right, trauma? No, okay. Memory, anybody? No, okay. There's a memory person there. Neuron? No, yeah, couple. Synapse, anybody? Okay, interesting. Receptor, now I'm pushing it. If receptor showed up in your word association, then that's very unlikely, right? I mean, it's a little, I sat doing this for a while. Well-being? Hallucination, anyone? Interesting, okay. Drug? Any drugs? Okay, there. Prozac in anybody's list? Okay. All right, so clearly I didn't figure out what most people stress in anybody's list. No? High on anyone's list? Okay. Throw out some words to me that you all had. I'll go here. Throw out words that you had.
So we had happiness, then it became protein.
Interesting.
Theater.
Excellent. So meat, food, theater. So now you're getting the associations, right? Let's go there. Any associations there that you were willing to share with us? What did you guys have?
Hormone, emotion, brain, feeling.
Excellent. Very good. Hormone, emotion, brain. Okay. In that corner, any associations you can throw out to us that we haven't heard so far yet?
Thyroxine, melatonin.
That's a biologist or a biochemist. If you did melatonin as a very good association, by the way, 2 steps further down than serotonin, but anyway, that's an unusual association that immediately picked up. Anyone here with an association?
Microbiome.
Microbiome. Good. Good gut.
Smiley.
Trigger.
Smiley, very, very nice association. I love that. Smiley.
Missing.
Missing. Okay. Any more associations that we want?
Yellow.
Neurotransmitter.
Somebody said yellow? That's interesting. That's really interesting. let me see, you might surprise me. I've had theater, yellow. This is interesting. This is what happens with word association. You start with what?
Experiment.
Experiment.
Exercise?
Absolutely, totally fine to have exercise in there as well. It's your own set of associations, and that's the good thing about it. It's free flowing.
I have Santa Claus.
That is interesting. Excellent. Okay, okay. All right. So we have. Anyone have regeneration? Cell. Okay. Now this is a biologist list. So you're going to get a biased list here: cell division, cell growth, cell survival. Antioxidant, anybody have an antioxidant in there? No? Okay. Wound healing, anyone? No, wouldn't expect it, but it's strongly associated. Immune regulation. Vomiting, if anyone has vomiting, they deserve to be shared that brownie with. Anybody have vomiting? Vomiting controlled directly by the serotonin pathway circuit that drives that reflex. You don't even think about it, it's a survival reflex. Imagine you ate something that you don't want. You want it out. Massive survival reflex, especially if it was poison. And believe me, when people were not figuring out yet what they were eating in the old days, before you figured out which mushroom was edible and which mushroom wasn't, you wanted it out. Right? You had to figure a way to get it out. So very conserved circuit. It's a circuit in the brain that you absolutely require. You need to learn how to vomit, or you need to just be able to vomit. And babies vomit very effectively. So it's not a learned task. It's a suppressed task. You figure out ways to hold it in till you get to the right place. So. Okay, gene expression, I don't expect that. Aggression, anyone? Anybody with aggression? Appetite. Somebody had gut. Yes. Microbiome, you had appetite in there? Okay, good. Interesting. Digestion, aging, longevity. Anyone with aging and longevity? Okay. Muscle contraction for anyone? Gut somebody had. Okay, the reason I put that in there is we tend to think about serotonin only from the bias of what it does generally to our brain. That's the lens we look at this molecule through. It's the lens that the scientists have also tended to look at it through, and certainly because they've communicated it out to the world at large, everyone thinks about this molecule, tiny little molecule, broadly doing something associated with your brain. But long before there were brains the way we knew them, and certainly this is beautiful 300 and what, 2 neurons? Something like that. Planaria, which is lovely, cut it in the middle, it grows back. Wouldn't that be nice? You know, it's a wonderful property to have regeneration. That's directly regulated by serotonin as well. Okay? Roundworms, these are not things you want in your gut, but they're there. And serotonin regulates egg laying, development. Mollusks regulates learning in this circuit. Arthropods, development again. So it's been there, and it's been our partner ever since there have been living beings on this planet for a very, very long time. Okay? That's what we're going to talk about a little bit today. So what we're doing is we're shifting the goal from looking at serotonin the way we saw it to the serotonin that is doing its moonlighting job. Doing something else than what you normally and standardly think about. But before we do that, we have to think about when did our species start even thinking about serotonin. Okay? So right there is Vittorio Ersparmer in the 1930s, an Italian scientist, and he isolates it from the gut. Okay? So that's, somebody said gut microbiome, somebody said appetite, somebody said gut, somebody said probably not digestion, but a lot of people did say something about the stomach and the gut. The only way food is going down is smooth muscle contractions. Smooth muscle contraction directly regulated by serotonin. Tone of muscle regulated by a factor found in serum, so serotonin. Okay? Wasn't called serotonin then, it was called enteramine when he found it from the enteric, from your enterus, so essentially your gut, right? Then along comes Irvin Page's lab, and so this is happening in the 30s, this is a little bit later. All this happens in the 50s, and they're isolating tons of serum, which they get from coagulated blood, which they carry, and they collect 900 liters of serum to find this tiny little molecule. That's how they had to start. That's their starting material. To find this tiny little molecule called serotonin, and they called it serotonin. They figured out in the 50s that it's the same molecule. So it was already known, just here it was called serotonin, here it was called enteramine. The drug companies figured out the structure. So it's Abbott that actually figured out the structure. You have to slip back in time a little bit to the 1940s, and you have Hoffman synthesizing molecules from plant-derived ergotamines, which are like serotonin. One of the molecules they made was LSD. LSD was the molecule that led to people thinking, oops, this thing regulates how you feel. It regulates your entire sense of experience because they took it. Yeah, it's pretty, that's how experiments were done in those days. They tried them on themselves in many cases. Not something I would advise, but anyway. So this is 1940s, late 1940s and 50s. By the 60s and the 70s, drugs that regulate, or rather the precursor drugs that eventually became the mother drugs for the whole antidepressant industry, were already in place. And many of them hit this particular chemical, changing levels of serotonin in your brain. That's why we so strongly associate this molecule with how we feel, right? So this is where that actually started. But in all our history of any molecule, we tend to forget that there is indigenous knowledge, because very rarely does that get discussed. We often have a scientific literature knowledge because it's been published, but there is usually indigenous knowledge that is a lot older than that. So the shamans in South America used to boil a component from diverse plants. It's called ayahuasca. Ayahuasca is the tea. The active components of that are things that resemble serotonin in structure. They alter states of sensory perception. It's still used. Ayahuasca tea was given by the shamans, and that is actually serotonergic modulation right there, okay? There are multiple molecules that have been used in Ayurveda that also hit these pathways, rezapine being one of them. Eventually was responsible for discovery of many other neurotransmitters like serotonin. And this thing here is called magic mushrooms. And so like I was discussing with you, people were eating mushrooms, people were also poisoning themselves with mushrooms and puking them out. But people were also finding out that if you ate some mushrooms, like LSD, you altered your brain state dramatically. And that molecule is this thing here, psilocybin, okay, which is structurally similar to serotonin. Okay, so how do you make this? Are we, capable of making everything in this pathway ourselves? Plants are, but none of us in this room can synthesize serotonin unless we start by eating this. That's an amino acid, essential component of proteins, many proteins that contain this particular amino acid, tryptophan. Tryptophan gets oxidated, gives you this molecule, gets decarboxylated, gives you this molecule. Lots of things have tryptophan. Now, if I tell you all, we're all going to go on a 1-month diet without tryptophan. So we're going to remove it from our consumption completely, right? Are we all going to get depressed? No. But if there are some of you in this room who carry a genetic predisposition, or if there are some of you in this room who have had a prior episode.
Sorry to interrupt this. So we've been able to establish a live link.
Okay.
We are starting it. Would you mind giving a 2-minute summary of whatever's been missed so
Sure.
that people joining in
Sure.
can
Absolutely.
yeah?
Yes.
Quick, just 2 minutes.
Okay, guys, this is going to be trailer rewrap now, very fast. All right.
You guys don't mind?
No,
Okay.
The online audience, so that they don't suddenly figure they're coming in the middle. At least they
Okay. So we are talking about a molecule called serotonin, which we usually associate with the brain, but much of it is in many other places other than the brain. To make serotonin, and we just played a word association task where we were talking about what do you associate with the word serotonin. And many of you gave me an answer which was associated somehow or the other with the brain. Thankfully, some of you also said other things, which was really interesting. I love the yellow answer, something completely out of the blue, but it's true, a jaundiced view of the world or a blue view of your universe is in some ways regulated by serotonin. It changes the way you perceive the world. So we are now going to talk about how you make this particular neurotransmitter. So we lost the ability to make it. Our plant cousins on this planet make plenty of it. We don't. We have to eat stuff that has tryptophan to actually make serotonin, all right? So for us, we must be eating this. And if we don't eat this, we'll eventually deplete the amount of serotonin we have in the brain. So I was just telling you, what if we all in this room went on a tryptophan-free diet? It's doable in principle. Right now, everybody's changing something or the other in the diet. You have a keto diet, you have a whatever diet. So if you can also go on a tryptophan-free diet, I wouldn't advise it, but anyway. So if you go on a tryptophan-free diet, you're not necessarily going to get depressed, but you're going to lower your levels of serotonin. If you have a history of depression, you're more likely to manifest with a full-fledged depressive state. If you have a first-degree relative with depression, it is also possible that your risk goes up, right? If you have previously suffered a depressive episode, it's more likely to precipitate a depressive, but it's unlikely to cause it in its entirety in the absence of all of these things. So it's not just levels of serotonin, it's the system in which the levels of serotonin are being changed, okay? So that just gives you a bit of a handle. All right. Now we're going to do another experiment. Those of you who have brownies with you, how many people with brownies? Okay, share a little bit if you don't mind. Yeah, there's people with cupcakes. Excellent. People with bananas. Okay. So the rest of you can just look at each other and guess. The ones who have this are going to tell me what percentage. You're going to write it down in your little whatever notepad you have or in your phone. You're just going to guess what percentage of serotonin in your body is here and here. And those of you who have the walnut brownie and the banana walnut muffin and the banana are going to guess whether you have more here or in the banana or the walnut muffin or in the banana walnut muffin or walnut brownie. Okay, guess away. Give me percentage distribution between this and this. So 100%, how much percent here, how much percent here? Okay, talk to each other, take a guess. Okay, we have an answer here, someone saying 90% in which? 90% here, 10% here. Okay, anyone else taking another guess over there? Okay, I can't hear, so you're going to have... Okay, you know, I've let this out. Yes, it is much more in gut. We'll now see if anybody gets close to predicting the percentage. I'll say 90 is right. 90 is right. How much over here? It's not 10, it's 2. 1 to 2. Okay? So now let's take a guess for the guys who had the banana. Anybody have a sense of how many milligrams of serotonin you have in banana skin? Anyone wants to take a wild guess? Skin. Yeah, you don't eat the skin, but the monkeys did. Yeah, they weren't doing this always. They were eating it, right? That tells you skin is quite interesting in many things, including potato and including banana. So skin is not what you necessarily always want to throw away. You may not want to eat pineapple skin, but many other things you may want to even consider. Okay, anyone want to take a guess? How many milligrams in banana skin? 10. Okay, you're in the right zone. It's somebody else want to change the factor there? Okay, you're still in the same factor range. It's 40. 40 milligrams in banana skin. Now let's take a guess. How much in your hippocampus, which is the part of your brain that's responsible for learning, memory, states of being? Want to take a guess? How much? Per banana skin. One skin. The entire banana skin, which you can do it as per gram of banana skin. So you can do it as eventually how much ever you get from one. I don't know how many grams you have in banana skin, but it is one banana, that's the 40 milligrams that you have. Yeah? I don't know how many grams you would have after you mushed up banana skin and weighed it out. In the hippocampus, any wild guesses? 0.4 milligrams. Okay? So that tells you it's a factor of 10 difference in your hippocampus. Your hippocampus is actually quite a banana-shaped structure as well. Significantly smaller. It's not the size of the whole banana. Maybe half an elaichi banana, even smaller than that. Really tiny. But that's the sort of range we are talking about. So we already know that we spend a lot of our time thinking about serotonin here, Most of it is here, and a lot of it is outside us, which we barely pay much attention to, okay? Anyway, the starting material is all outside us. We've lost the ability to make it without the starting material. We don't make tryptophan ourselves. Okay, so now let's look at this from the point of view of when life started, right? So this is origin of life. Somewhere here, about 3 billion years ago, we are not there, okay, we weren't around. Our ancestors weren't around. Anything like our ancestors was also not around. That's where serotonin shows up. Serotonin is also called 5-hydroxytryptamine, but that's serotonin, right there. So early, the single-cell organisms, amoeba, by the way, has a ton of serotonin that you never think about. It helps amoeba to eat, yeah? So amoeba has it. So you have lots of single-cell protists that have it. Algae have it. Out here, you going, this big thing, plants, of course have it. Chock a block full of serotonin. Of course, they have their own ability to make tryptophan. Somewhere here, we lose the ability, our ancestors lose the ability to make their own tryptophan. So now we have to eat this and other things that are out here to get our tryptophan. So we get it from plants, we get it from meat, we get it from all of these other sources, right? We've lost the ability. So we've lost, this whole component has lost the ability to make its own tryptophan. Here's where that happens, and then we have to eat the stuff that came, in a sense, evolutionarily before us. Lost the synthetic enzymes. We lost the synthetic machine. With many things we have lost. So for example, you and I cannot detect a lot of the visual spectrum, which is beyond a certain, which other bees can, for example. You can't hear things that a dog can, for sure. You can't smell a ton. We've got lots of pseudo-odorant receptors. We lose things. We keep what is really evolutionarily salient to us. Yeah? So we can eat this, right? We figured out ways to eat it and cook it and survive despite not being able to make our own tryptophan. So it shows up here, and this is how far back it is. So it is there in things that don't have a brain. There's no brain. There's no nervous system. There's serotonin. Okay? And so there's a ton of serotonin in things that do not have your standard idea of the nervous system. So what was it doing then? Why was it around in large quantities, and what did it do? And this is a question that you surprisingly don't find too many neuroscientists asking. Partly because we're a bit obsessed with what that little 1 to 2% does in the brain. I certainly have spent the last 30 years of my career looking at serotonin in the brain, okay, not looking at what it does elsewhere, what might it have, its original function have been. So few people have thought about this. There have been ideas like this that have floated around, but it has not been as much an avenue of investigation. So what does it do? And does it do in the brain what it originally started off doing? Did we just co-opt it, in a sense, into neurons and then say, okay, you were doing this and you were doing it well? Evolution doesn't waste stuff. If you're doing it well, and you're doing a good job of it, we'll add new function, but we'll keep the old function, right? So we tend to reuse old recipes over and over again, which is why our body maps have used a developmental plan that's been going on all across vertebrate evolution. And many, many of the things that are the building blocks are the same for flies, for invertebrates, and for us. That's why you can study multiple model organisms and get insights for ourselves. So the first step for tryptophan to start becoming serotonin is it needs to have a hydroxyl group added on. So you need some source of oxygen. And when you think all the way back, it wasn't a very oxygen-rich universe at that point, right? Who makes its substantial amounts of oxygen? Yep. So think about, what am I showing you here? Any ideas? Algae. Yeah, I'm showing you tons and tons of algae, blue-green algae, okay? Showing you some nice-looking fungi, right? So, which also can produce serotonin at high levels. So, when life evolved, it had to find eventually a way to generate energy. For any work to be done, there was a requirement of energy. And what is our entire source of energy for us? Yep, sun. Absolutely, right? That's our source of energy. So you're going to have to trap sunlight somehow. Most of the trapping happens through tryptophan. Tryptophan has an indole ring which allows it to really trap light and use that to transfer electrons down an electron transport chain. That is the beginnings of photosynthesis. So you are trapping light, using this, and your byproduct is going to be what at the end of that? Everybody learned this in school. Everybody remembers this. What are you making at the end of this photosynthetic pathway? Glucose. And what are you going to do with that glucose? Where are you sending that glucose? Yes, but you're going to use that glucose somewhere usually to make energy. Do you know what that structure is called? You're going to make ATP. Somebody said ATP? Mitochondria. Absolutely. Another system with an electron transfer chain. Right? So you trap light, use tryptophan in the photosynthetic centers to eventually generate oxygen as your byproduct. You're also going to be making tryptophan in the very same structure. It's your rich center of tryptophan synthesis. Okay? So you're taking this light, trapping it, making tryptophan byproduct, you're going to eventually start making serotonin as well. Okay? That's your starting material. Glucose comes out, oxygen is relevant, oxygen is going to be used to oxidize things as well. Right? So you now have that glucose that goes into mitochondria, eventual byproduct being ATP. Again, that's energy transfer down an electron transfer chain. And that gives you breakdown products with ATP being generated as a byproduct. That's your energy, currency, right? So these two are co-evolving. Right? The minute you found a way to trap energy, it's a two-edged sword. You have the ability to trap energy and do electron transfer. You also produce free radicals. So that's a byproduct. You can't help it, right? So superoxides, hydroxyl radicals, you're going to have all of these, and radicals, free radicals, have a higher tendency to interact with anything that's there, eventually building up what? Damage. Right? So if you sat in UV for long enough, you'd roast yourself, right? And you get burnt, right? If you did a whole bunch of things that produce bleach, hydrogen peroxide, will eventually cook your cells if you leave it in it for long enough, right? So free radicals will cause damage. So at the same time as you figure out how to trap light, you're going to have to find a way to control the number of free radicals you have floating around. Otherwise, all this generating of energy is useless if you're going to die at the end of it, right? So plants are chock-a-block full of serotonin. That there can have up to 400 milligrams per kilogram. All right, that's walnuts. Nobody's eating a kilogram of walnuts, but it's telling you what an interesting source that is. I have to remind you, though, that the serotonin you eat is not going to your brain. It's the tryptophan that you eat, the L-tryptophan, that allows you to eventually make serotonin. It's just interesting that there is that much serotonin floating around in plants that we don't normally even think about, right? Okay. So here's this idea, and this is really from people like Efran Asmitia at Sunny Buffalo, who really came up with these ideas of how sunlight trapping, and so here's where you would have tryptophan. By the way, associated with tryptophan biosynthesis, also a hormone called auxin. You were originally algae, maybe a little bit of a moss, maybe a fern. Eventually, you have the sycamore tree, and you have those huge giant trees. You have a banyan. How did you go from this tiny little plantlet to this big structure? You got to have hormones that drive it. Amongst the hormones that drive it is a molecule called auxin, which is also tryptophan derived. So that's a circuit that is going to eventually give you growth. Okay, so it's a growth promoting hormone. Byproduct here is serotonin. Serotonin also modulates growth. If you take a leaf, cut it off, it starts browning. If you apply serotonin, the browning is reduced. Interesting. Wound healing is what we also do with serotonin. That's a wound for a plant. So it's interesting how these functions tend to get conserved. All right? Okay. So now we've got trapping light with the goal to generate energy. And your generation of energy, so you trap light. If there was a chloroplast here, you trap light. You eventually put out glucose and oxygen. You're going to use that here to burn. It's a combustion reaction. You're going to burn the glucose with oxygen to give you your byproducts. Okay? So that's a combustion reaction. So out there, your byproduct is ATP that allows you to do work. So many, many things that it's a plant hormone almost. But years ago, people had wondered, is it an antioxidant? Does it reduce oxidative damage? And this is where we come back to the original question. So this is just something that we have discovered relatively recently. It builds on a lot of other people's work, but I thought I would share this discovery with you as well because it's relatively recent in the lab. Does it do in the brain what it originally started off doing? These ideas are in multiple other systems. Why would it not do in the brain what it did in the leaf, what it does in the gut, what has been suggested to do in the muscle? What makes brain cells so unique that it doesn't continue to also do this in the brain in a sense? But it just never had been looked at. So here's the question. That's Sashena sitting right here in the front row. So this is Sashena's work. I get to stand here and talk about it, but it's all her work. So we asked the question, does serotonin regulate mitochondria? Serotonin is critical for plasticity, growth, differentiation, aging. This little molecule, this little organelle also does many similar functions. So we started asking about this relationship. And the people who sort of work together, so that's Sashena, the postdoc, who we've enjoyed thoroughly working with. Sukrita, master student in the lab. Ullas, who's my collaborator at TIFR. That's my dad. So I had the great fun of collaborating with my father on this project, which is rather rare, but a lot of fun. And this paper just got published. I'm not going to show you data. I'm just going to tell you what we found. And then we're going to open it up and talk, okay? So serotonin, it turns out, in neurons, actually allows you to make more mitochondria. Make more mitochondria. You also get more energy currency for the additional mitochondria that you have. So you have more mitochondria, so you have more ATP. But for every mitochondrion, your ability to produce ATP is also increased. So it's like having more energy producing devices, but they're working a bit more efficiently, okay? This should be bad news because if you make more ATP, you also produce a lot more free radicals and oxidant damage. Turns out that while it's boosting this, at the same time, it's boosting enzymes that scavenge and clear up all those oxidative species. So you increase the number of mitochondria, but you don't allow damage to take place. Here's what it looks like. Here are neurons growing beautifully. Here are neurons that have seen serotonin, and you end up with significantly more mitochondria in them. And that's the amount of ATP that you make as you increase the amount of serotonin that they're seeing. And we figured out how it does it, the receptor through which it does it. By the way, that's interesting. That's the same receptor that LSD hits and psilocybin hits. So it's an interesting idea that that's the pathway that it eventually does it through. This is what we figured out. This is really intermediate detail that you don't need. But serotonin through this receptor sets up a program that has been used in muscle, has been used in heart. We didn't expect serotonin to be controlling it. This pathway was known, but the fact that serotonin controls it through this receptor in the brain was not known. And why does it matter so much for neurons? Neurons are the cells you live with the rest of your life. Your skin, you're shedding. You're not going to have the same skin in a few weeks. Your bone is going to replace itself, right? A lot of your liver is turning over. You can't turn over most of your nervous system. What you've got, and you hold on to, which means you have to take really good care of it. So it's the system that stays with you your entire lifespan, which is why you don't want it to be damaged by free radicals, to be sensitive to death. If you lose large numbers of neurons, you know what happens. We can't replace them easily. Right? So this is what we found. And I'm hoping that what we've done is given you a new word association. Serotonin regulates mitochondria, gives you more mitochondria, more energy production, and allows you to chew up or clear out the free radicals made by mitochondria during the process of energy production. So serotonin will clear that off. And now if you take neurons and bathe them with things that will kill them through free radical damage, okay? So you take neurons, you're putting things that would kill those neurons, but they have seen serotonin. Serotonin will protect those neurons significantly. So you have a very strong neuroprotective action of serotonin. Why is this relevant? We've always wondered why serotonin helps you buffer stress, why serotonin is, in a sense, a positive modulator of your circuits. We have one possible way via which it allows these neurons to stay healthy and buffer any other damaging, stressful cues that it is seeing, right? Your levels of serotonin go down with age. Your serotonin levels go up with exercise. Yeah? Your serotonin levels change as sunlight dips, right? They seasonally alter. So you're now beginning to think about what this neurotransmitter may be doing. What you do, what you eat, your environment can regulate the way your serotonin is released, levels of it. It's not very surprising then to imagine scenarios in which you can change levels of serotonin, and that can directly impact how you buffer stress, how resilient you are, but it's from an old, conserved, unexpected function, right? A function that's been around for millennia, long before there were brains, long before there were neurons, long before there was even a nervous system. So this is where we've done the work out there. There's a little hut right there, should be right there. You can't see it, but that's where our lab is, and that's the team of us, and of course our funding support from DAE. And I left plenty of time for questions, so we can just have a freewheeling chat.
Okay. I see lots of hands. I'm sure you have lots of questions. Vidita, please be kind enough to repeat the questions because
I will.
You are on the live stream. So yeah, let's start. Your hand was up there first. Yeah, you were there.
How do you, in rainy season, because there is no direct sunlight, and how do you maintain serotonin to its optimal level?
Yeah, so
apart from exercise.
Yeah. So the question is, in the rainy season when it's rather dark and gloomy, how do you maintain your levels of serotonin when you're not getting the standard rhythm of light? I don't think anyone's looked at it with monsoon in India. The thing about Indian monsoons is that we are still never in the zone that, for example, Scandinavia goes through, where it is dark and truly dark, right? We would be dark during periods of time, but then when the clouds clear up, we go right back to radiating sunshine. It's remarkable how used to we've gotten to that sun. When you don't have it, and you really don't have it, like you have something like 7 hours of sunlight in a month or 2 months, then you see strong seasonal affective disorder, which is the depression that is associated with a loss of exposure to light. People do light therapy, and it does work, right? So there's no question that, and a lot of times we don't think about it. You go to an office, you've seen no real sunlight. You have had this ambient light of white light the whole day. You go back home, you're with the blue light or whatever other light that is coming from your phone. You don't switch off your lights in a regular circadian rhythm, which drives the secretion. So serotonin's high during the day, starts petering down. Melatonin starts coming up before you go to sleep. So there are the rhythms of these neurotransmitters. Now, if you are going to be in 24 hours of non-sunlight driven light, you're going to have an impact on your nervous system in terms of your rhythms. There's no question about it, right? So there is a lot, besides the vitamin D, which you can see, most of us, if we test our vitamin D, will be in deficient levels. We're all vitamin D deficiency. So how could we have an epidemic of vitamin D deficiency, that too bang it near the equator? What will happen to vitamin D levels elsewhere, right? So in a sense, I would say that there's, of course, exercise, but there's the mandatory. There was a reason why people went out for those early morning walks or went out and sat in the sun and sunned themselves for some time. If you just do not put that in your rhythm and you do not allow the light, so our entire circadian clock is light entrained. There's a free running clock, but light entrains our clock to follow the rhythms that we generate from using sun. So I would say you will eventually have an impact if you're completely without effective sunlight. That's one of the reasons why it's so high in countries where light is not, especially for months in winter. I hope that kind of answers your question. There are not too many other sources to elevate your levels of serotonin. You can do it. Exercise is one good one. The other one is social interaction. Yeah? So social isolation is one very effective way to reduce your serotonin, signaling effective serotonin. So we are a very social species. We get a lot of positive reinforcement from our social interactions. And that drives up serotonin as well.
Yeah, just to carry it forward, circadian rhythm, what you mentioned, what exactly is the interconnectedness with serotonin?
Okay. So with serotonin, so it's a much more easily identifiable driving of melatonin because there's a direct input from your eyes to the suprachiasmatic nucleus, which goes to the pineal, where you secrete melatonin, which is then regulated by the clock. But it turns out that serotonin production and serotonin firing is, so most of the serotonergic neurons you have are in your midbrain. And they have a rhythm of firing. And that rhythm of firing is changed based on the 24-hour, so the 12-hour shift of light, day, light, day. So you have a circadian rhythm of the firing rate of those neurons. Where the input that comes from that drives it is perhaps as less well known than what regulates melatonin. But many of these cells have their own free-running clocks. So every cell has its own clock, and then there are master clocks that control and sort of coordinate all clocks, right? So where does the drive come to the serotonergic neurons? Perhaps not as well known. Likely to be hypothalamic input. There is hypothalamic input going back there. The hypothalamus receives straight input in from your eyes. But if you had no input at all, you would still have a clock. It would just not be coordinated with the, so you still have a clock. It would just not be responding to what is the variation of light outside.
Okay. This talk was so interesting, and I was listening to it, that I forgot one very important thing. We always are supposed to take a break for chai. Okay, so chai doesn't happen without chai. So let's take a very quick break. There is chai outside. There is chai outside. Get a quick, I'm sure you have lots of questions. Get a quick cup of chai and come back. We will continue this discussion. If you are following us live, just give us 10 minutes. We will be back again with questions for Vidita. Okay, so just grab a cup of chai and come back.
Do we wait for Arnav to come back in, or do we hold it? But then we coordinate the question. I think so.
Everyone had some chai, they might have gotten some happiness and some happy symptoms.
Yeah, all that sugar.
Comparative analysis, how many people actually were able to eat that walnut brownie and gain some happiness? Control experiment. Some weren't, some were.
Yeah.
Yeah, so we are back after the chat and we'll start with the question round again. So anyone who has a question?
There's one there.
Hi, so thank you for your talk. It's been very interesting so far. So my question is, we have been talking about if the serotonin levels are less, this may happen or that may happen. So there's a flicker in my mind that what if we consume more amount of tryptophan? Will it have like similar effect that of LSD? Because we talked about that it extracts that. I was just wondering.
Can you get high on banana?
Yeah. Okay, you just hit the $1 million question, which is, I'll repeat it, which is if you have enough L-tryptophan, will you eventually start hitting receptors like LSD hits specific receptors and perhaps hallucinate yourself into another state? A little unlikely, but the receptor that regulates those hallucinatory states is the same receptor that's associated with schizophrenia. Okay, so when you say, I don't know how many of you have watched the movie A Beautiful Mind. Yeah? So you know that we are in principle capable, our entire universe is a constructed percept that our sensory system generates for us, right? I can't see what a bee sees. So I'm seeing the universe with my opsins, and it's limited by the visual range that I can actually detect. And I can't see in the UV range, for example, so I can't see a flower the way the bee sees the flower. So our world is the world we create, our nervous system creates for us. In individuals with schizophrenia, there's one of the ideas is that serotonin hits the serotonin 2A receptor and somehow alters you into a hallucinatory state, which it doesn't do in most other individuals. However, if any of us was to take LSD or psilocybin or the drug that we've used in our experiments, which is a clean drug for that receptor, DOI, we would also hallucinate, which means that receptor is capable of going into a signaling state that gives you hallucinations. Dimethyltryptamine, which is again a tryptophan-derived molecule, is the main constituent of ayahuasca tea. Ayahuasca tea is drunk by the shamans to presumably connect to other worlds and universes, and that is a strong and potent hallucinogen. So the question is, what makes serotonin capable of driving a hallucinatory state versus not? Nobody knows the answer yet, right? It's one of the things that fascinates us, drives us. I have graduate students who are asking exactly this question. Why is the same molecule going to give you hallucinations in some cases and not in others? Little unlikely that 5-HT would give you that kind of effect. Certainly eating a banana, the 5-HT doesn't cross the blood-brain barrier. You would actually have to get large loading dose of L-tryptophan, which is going to compete with other amino acids for the same transporters to get into your brain, right? So you could probably drive up a certain amount of an increase in your serotonin levels, but it's unlikely that would ever take you and tip you into that state. Something that is capable of binding to the serotonin 2A receptor that can take it into that hallucinatory state, we don't have the answer. We know what eventually happens to the circuit, but we don't know at the very initial signaling step. We think we may have found it, but we don't know if that's true. We think we may have found some differences, but we really don't know yet, right? So I would say no, eating all the bananas in the universe is not going to do that to you, certainly. But it is interesting that people use these as exercises via which people drank ayahuasca tea to get access to other sensory experiences. Now, I do not want to convert this into you thinking, perhaps not a bad idea to have some LSD, yeah? Keep in mind that it's one of the interesting molecules that one single exposure to, right, a single exposure to can evoke what's called perceptual flashback disorder, which is you had it maybe when you're 20, you're 55, and suddenly you have a full-fledged hallucinatory experience without any LSD in your system. It's because it rewires circuits so potently that a past exposure can, in the future, at random, re-evoke a full-fledged hallucinatory state. And all hallucinations are not going to be, how wonderful is this world? It could also be a really, really negative experience. And so this is what people worry about. There's a controlled way to just take the circuit into a plane and a state where you are just in a positive state. I would say probably doing the work to get there is better than actually taking the pill. And presumably, individuals who do certain practices can get their nervous system into some of those states. For example, if you and I concentrate on a task, we'll get into gamma rhythms. Individuals who do TM, transcendental meditation, can go into gamma rhythms much more easily. So yeah, you can train your network. It's like running a race. You can train your muscle to run the race. You can also train your brain network to modulate the states that it can get into. But I would say the physiological regulation is far better than the drug-evoked regulation. You don't have control over what the outcome will be. Yeah, that's the scary part of these class of drugs.
Yeah, at the back, then you said the way we perceive the world, every individual perceives in a different manner, and it's a function of what goes inside in terms of chemical reactions. So, in a nutshell, are we just a bundle of chemical reactions, slaves to chemical reactions?
We are a bundle of chemical reactions for sure. And you know, it's true that your purple may not be my purple. Okay, we will say, I see purple. I mean, you and I cannot have a complete understanding of what your purple and my purple is. It might be slightly different. We broadly called it purple, and you and I are agreeing to call it purple because it's falling in some broad zone. But there will be somebody who says this purple is lavender-esque versus mauve-esque, right? So you will have slight differences in your perceptual state, and eventually your percept is an outproduct of multiple sensory reactions that produce a sense of percept. Now, this is where neuroscience starts struggling, because we have a lot of understanding at the very beginning. What happens when light strikes the photoreceptors? What happens at the next? How do you create percept? It's something that we can't even tell you yet. We're dealing, so it would be very easy for me to say, yeah, it's all just biochemical reactions, but it's clearly an emergent property of a network. We still don't know how that eventual percept is created, but I mean, you can also say that you can drive those chemical reactions, right? So that's where you have direct control with how you can modulate you could choose to do X, which can drive your chemical reactions in a particular way as well. So yes, I think it's a nice reciprocal relationship.
Many older people, when they move closer to death, maybe a few months before or maybe 1 year before, they tend to hallucinate. It has, normally when the body is about to die, does it elevate the serotonin level?
No, actually not. I mean, in fact, if you just look at the natural process of aging, serotonin levels go into steep decline as you age. So in fact, that's been one of the interesting questions to ask, which is serotonin goes into steep decline. Mitochondrial dysfunction also shows up round about the same time in that sense and overlap. And so that dysfunction and decline is actually seen with the natural process of aging in any case. I want to tell you that we all think we are not hallucinating. But that might be a matter of slight debate. There's a substantial discussion now about how much of ongoing baseline hallucinations you have which you are not even aware of. So there's a debate on this. There's an ongoing debate on whether, what is reality eventually? It is what you see. And for the person in Beautiful Mind, they saw a person there. Now you can't say that's not your reality. I'm seeing it. My nervous system is seeing it. Just because you don't see it, I can't say that it doesn't exist for me, right? So there's been a lot of debate as to whether ongoing baseline low-grade hallucinations are just part of our living experience and we don't even know because they don't really impact our life substantially. When it's a major auditory hallucination or a major psychotic episode like it happens in schizophrenia, then it disrupts your normal functioning hugely. And so then you pay attention to it. But otherwise, I heard something and you're thinking, did I really hear something? I don't know if I heard it. I don't know if it was out there, but I heard something. And then maybe you heard something because the circuit fired without the sound outside and you heard it because you created percept. So yeah, there's an ongoing debate. It's a difficult one to tease apart. These are not easy experiments to do in animal models, so we get very restricted. The sort of subjective experience is something that is human in its description, in a sense.
Yeah, go ahead.
I just want to continue with the previous question before this. You said that something backfires and rewires the circuit, right? So, is it the same? Are you referring to PTSD?
No, I'm referring to the fact that when you take any two synapses, which are connected, so here's a synapse, presynaptic, postsynaptic, learning is a rewiring of the strength of input capable of giving you an output, okay? So here's a neuron, fires, gives you a particular response. Let's say this neuron has been conditioned and learning something over and over and over. Eventually it starts giving you stronger and stronger responses, right? So then you retain that information over a period of time, and if you do this over and over again, ensembles of neurons retain certain memory information. With LSD, what happens is at synapses, in the absence of the primary sensory experience, it causes local changes which make you think there was an experience, but it is just producing it here locally without the experience. So it's as good as having had the experience, because the brain sees it, I saw the experience. You don't have anything outside. Locally, it's like having had that experience, right? So you strengthen synapses and circuits without the context, without the real world context. PTSD, serotonin may or may not be doing this in PTSD. It's not different from PTSD in the sense that that is also associative learning. For example, your associative learning largely probably in the amygdala and in other circuits. Post-traumatic stress disorder, so let's say you went to war, two people went to war. They went through a severely traumatic experience. One individual has constant flashbacks of it to the extent that it affects their ability to function. The other person same experience, did not develop PTSD, right? So we don't understand why it is. So in fact, we've been writing precisely about this the last few days. We're discussing a manuscript where, for example, let's say I take a box. If you were to do this in a rat, right? And you put a rat in this box, this has a grid. Now you pair a sound with a shock. Over a period of time, classical Pavlovian conditioning, you don't need the shock. The sound will give you the full-fledged fear response, right? When you start generalizing this randomly to additional environments and you don't even learn how to get rid of this. So now if I keep giving the sound without the shock, eventually you'll say, okay, no, there's no shock coming. I should forget about this. So you override, you extinguish the fear. Failure to extinguish fear, generalization to contexts where that experience has not happened is a classic hallmark of PTSD. That is also circuit modulation and learning. What I'm saying with LSD is at the cortical level, imagine multiple sensory inputs coming into the cortex. Right? That's how you see, that's how you hear, that's sensory experience coming into the cortex. Now you have no external change, but you're still producing all those responses. So you feel you are seeing or hearing things because your brain is seeing and hearing things without any real world context. Randomly, years later, without any LSD on board, you can recreate that state because that network just decided to get activated out of the blue. So now you have a full-fledged hallucination. You've not taken LSD, there's nothing outside, but you are hallucinating. This is known to happen, it's called HPPD. It's because the circuit has been predisposed to remembering a state. So it is eventually similar cellular mechanisms at the level of the neurons. The effect is not the same. The underlying cellular molecular mechanisms may be common. The effects in PTSD and LSD-evoked hallucinations are very different, but the underlying ABCD machinery that does it is very similar. Yeah, different circuits. Okay.
You mentioned about you are controlling the chemicals. So now in that context, so is it that the thoughts are what generate the
Wow.
That is first part of the question. Second is, in that case, does meditation have a role? Because there again, you mentioned about the gamma resonance.
Yeah.
And the third part was about
I'm going to lose track. I have to repeat all these. Sorry. So the first one is which one is the thought driving the chemical or is the chemical driving the thought? Chicken and egg. Don't know how to dissect that, right? Thoughts are eventually a byproduct of your nervous system, which means that you have to have certain chemical neurotransmission to have the thought, but the thought is also capable of changing that very same nervous system. So this is chicken and egg. It's a serious chicken and egg problem because it comes down to what is conscious thought. We don't have understanding yet cellularly, molecularly, or even circuit-wise well of consciousness. So we are going into zones which are complex in neuroscience. We are like still at doing ABCD, you're asking me about War and Peace Tolstoy novel. It's that scale. We're still in the journey of learning this, still at the beginning end. So we don't have an answer to that, but I would say thoughts are eventually a byproduct of chemical reactions, but those very same thoughts can modulate those chemical reactions. So there is a direct relationship. The second question was what? I forgot. Huh? Meditation. So meditation, I mean, if clearly some experiments have been done where people have started recording EEG patterns, which is what you can do in humans, fMRI, PET, etc. Exercise has such a profound effect on the brain. Why would meditation not, right? I mean, you go on a treadmill and you run and you go for a walk, and even walking on grass and the light and the sunlight has an effect. I would be surprised if meditation didn't. There would be no reason to believe that that experience would not and everything else does. I would actually say you're more likely to have an effect, especially if you do effective breath control. Given that breath control directly changes lots of arousal centers in the midbrain, which sit bang next to the serotonin neurons. All your pH sensing neurons are there. Acidosis in your blood responds directly to the manner in which breath is regulated. One of the first symptoms of fear is a change in your breath pattern. You know, so of course breath control will have profound effects on the nervous system. I would be surprised if it didn't. Do we know precisely exactly how it goes about doing it? Bits and pieces. We don't have a complete understanding. But I would say you will lose nothing meditating. You know, it's the same, like, it's in fact, I would say more powerful than exercise in some sense, because it also gives you the ability to bring yourself into fairly calm states. And so there's a very effective, powerful tool to that. It'll also regulate your endorphins, your endocannabinoid signaling. So I would say yes.
I just want to add, you can do this search online. There's a Harvard study said that if you meditate and run, because you run and meditate, both have a very different impact. So meditation followed by running has a far greater impact than vice versa.
Okay, we'll come back here.
Just a two-part question. First, kind of a statement. I just wanted a clarification on when you said when people do LSD or do DMT, they are perceiving an objective reality which is different. You're not saying the objective reality is changed. I just wanted to just make sure that people understand kind of that part.
You're perceiving a reality which is eventually a byproduct of your nervous system. Yes.
So you're not saying that the actual physical reality out there changes. Yeah. So the second question.
I mean, we will go into questions of what is reality, but that's okay. Reality is fundamentally a creation of your nervous system. Yeah, I mean, it is what you see and what you're equipped to see, feel, hear. It's within the limitations of that.
And the second part was when, say, people take medications like SSRIs, they don't end up at a particular part of the brain where they're supposed to be. They're bombarded all over the brain.
Yeah.
So there are serotonin receptors all over.
Yep.
So how does that affect the brain?
Well, it's like going in with a hammer. So first question is the objective reality question. I mean, is LSD changing your reality, or is it just what you're perceiving? It's, you know, this is a debatable, this goes into philosophical spaces, right? So we are now asking what is conceptually reality. I'm going to tell you that I think reality is what your percept allows you to create, not necessarily what is physically out there, right? So yes, that is altered, and so you see a world broader than what actually exists out there because your nervous system is creating that world for you. So that's the first. The second is SSRIs will elevate serotonin everywhere. Yes, Prozac will elevate serotonin. So an SSRI is an antidepressant that blocks the reuptake of serotonin back into the neuron. So eventually you end up bathing the brain with serotonin. You don't allow it to get cleared from the synapse. So you end up with serotonin everywhere. The problem with that is it's a hammer approach. Wonderful it would be if we said, don't activate the serotonin projection to the amygdala, activate the serotonin projection to the ventral hippocampus, activate the central, serotonin projection to the prefrontal cortex. Shut this down, activate this, can't do it. So we will activate it everywhere. One pathway is fear, another pathway is aggression, another pathway is control over fear. So you're activating the fear pathway and the control of fear pathway both at the same time. So you're going with like this and hoping that one will dominate. So yes, it's a bit of a problem. So first of all, for the longest time, we didn't know which pathway did what. Now we have an understanding that there's so much heterogeneity. This pathway controls fear, this pathway controls the shutting down of fear. So receptors are everywhere. There are 14 receptors for serotonin. They're abundant in the nervous system. You don't have clean drugs at the moment. That's just the reality. About people who are clinically depressed, about 60% of them respond to the drugs that are out there, 35 to 40% don't respond to anything. So that's just the unfortunate ground reality that we're currently living. I think psychiatry in terms of effective treatment is still not, it's certainly better than where it was, which involved digging a hole in the head and letting the vapors come out. So it's made a step forward. I mean, thinking it's 100 years ago, that is what we were doing. So but we're still not targeted chemical approach, only one pathway, far away from it. So yes, it's a very dirty way of treating a fairly complex disorder.
Is it like analogous to treating cancers with chemotherapy? Not a scientific approach.
No, chemotherapy kills.
Okay.
This is not kill. Okay. So it's a little bit, so chemotherapy will kill other cells along with the cells that you want killed, right? You can't help it. But in this case, you're also going very dirty. Does sweet food produce happy hormones, and what about bitter food? Okay, so this appears to be a pretty innate response. If you take a little baby and put sugar on its tongue versus quinine on its tongue, you will see a clear facial expression difference. So it's not a learned, complex, I like sugar and I'm eating my whatever walnut brownie. It is fairly innate. So yes, we all like sugar, right? So flies like sugar and the smell of rotting fruit, which is nice, alcohol fermented as well. So they go after that, right? So these are the sources of food, and they've, across evolution, those are cues we've been drawn towards. Sugar will give you a high, but that pathway it hits is more another neurotransmitter, the dopamine pathway, less so than the serotonin pathway. But dopamine is associated with reward, pleasure, activation of those pathways. So yes, I would say yes, it does, very strongly. Bitter doesn't give you exactly the same, but a lot of it that can be learned. If you've had the best Karela sabji made by your grandmother, over a period of time it gets so strongly associated with that experience that you will now eat your Karela sabji with great positivity, but somebody else might think this is foul. Yeah, so it becomes more learned because it's exposure and training, but sugar is pretty innate. Most people will say this tastes good. Okay, so the question is, why did we lose the ability to make our own starting precursor for serotonin? We've not lost the ability to make serotonin. We make it from an essential amino acid, L-tryptophan. We've lost our ability to synthesize L-tryptophan. Well, you know, somewhere in evolution, some ancestor of ours, long back, must have lost this ability by fluke chance, right? Mutations are utterly just random. And ate some plant and survived. Because if you ate a plant or you ate some other animal, you got your L-tryptophan. So it was not essential to your survival. You found another way to substitute for it. For example, we lost the ability to make our own vitamin C. But it co-evolved with color vision. So we know that we should eat colored fruits because they make, we get our vitamin C, but lot of other vertebrates. For example, rats have their own ability to make vitamin C. They make their own ascorbic acid. You and I don't. So the rats are the most successful, right? There will be many more very successful rats. They are doing their antioxidant activity at another level. We have lost that ability. But it's not been essential to our survival. So it's okay, we are managing. So a lot of it is, it's not like this is the goal is, should not think about us as this pinnacle of evolution. We are one branch on a side that is a relatively recent experiment. As long as the system doesn't apply a selection pressure that eliminates us, we keep going. Once a selection pressure comes where this has become absolutely essential, then we'll go. We are such a recent experiment in evolution. Yeah, no, it would be wonderful if everything was logical like that. We will not waste time on this. But plants clearly do this, and so it's usually rarely as well. We will create the most optimal organism that uses minimally. It's just you do whatever, random mutation happens, selection pressure is applied. If it survives, it survives, it thrives, it adapts. What? Sorry, I lost that. I didn't hear it. Interesting. Are dreams hallucinations? No. Dreams are, to some extent, in neuroscience vocabulary, a replaying at random of circuits getting activated in the brain. In many cases, that replaying is actually prior experience you have had. It's just that it is random. It is not always nicely related, and it seems to be an essential component for your system to learn. And so, for example, let's say I train you to do something, but I don't let you sleep. Every night when you go into REM sleep, which is the state in which you dream, I wake you up. Your ability to learn that is just going to go down steeply. But if I allow you to have REM sleep after a learning task and another learning task, you're going to consolidate that beautifully and retain that memory. So REM sleep seems to be almost an essential requirement for the nervous system to now say, okay, I'm going to just randomly recreate, use and consolidate ensembles of neurons in the brain to fire together to retain certain information. So you feel like you've hallucinated because it made no sense. It's like you could be running at full speed and jogging in place in your dream. It doesn't make logical sense. Your recollective dreams is anyway some minor fraction of how much dreaming you've done. In many cases, you don't even recollect what you've been dreaming, but you don't remember anything. The last little bit, maybe something comes up, right? So no, it's not the same as a hallucination. A hallucination happens when you're awake, and for you, it is reality. It is a full-fledged reality. It is not a feeling of this is not real.
Okay, wait, not too many hands up. I know you've been there for a while. So Green Tea, yeah, go ahead.
So does music therapy balances the serotonin level? Because this is one of the environmental factors, and research has been done on this factor basically.
Music therapy balancing serotonin levels. I have 3 people here in the front who I will ask, do you know any evidence where people have measured serotonin levels after music therapy? Not that I know of, so I can't give you a well-framed answer to that. I have no idea. I mean, of course, people have done stuff like this with rats where they've played classical music versus rock. So, I think this was more for the entertainment of the graduate student than for the rat. But people have done those kind of experiments and seen that certain tonal quality seems to improve EEG rhythms, etc. But I don't think it's been looked at with serotonin. With? Okay. I can't think of a paper. I'll repeat the question. Is there a difference in the release of serotonin when you see artificial light versus natural light? You know, the problem with serotonin and measuring serotonin levels in humans is you have to get it from CSF. CSF requires you to have a lumbar tap. You can detect blood serotonin levels. That's not going to tell you anything about brain release. It's going to tell you about platelet and gut release and other release. So this is not an easy experiment to do. But in rodents, people have looked at circadian rhythms of serotonin and melatonin release. And so there is a clear circadian rhythm that is usually done in an animal house, right? Which is all artificial light. There's no sunlight for the animals in the animal house. So it's a good question, but given that light is such a strong entrainer of the clock and the quality of life with artificial light versus sunlight varies, I don't know. I mean, now it's a guess. Yeah, but we're not on evolutionary time scale. This is last 150 years is not evolutionary time scale. Absolutely. I mean, what we are doing, for example, this constantly, we're rewiring our nervous systems, for sure. And the more our entire social universe moves into this space and less into this space, we will rewire what is socially acceptable frameworks of behavior. So there is a selection pressure applied by this object. Absolutely. So yeah, of course, but we are still dealing with behavioral time scales, not evolutionary time scales.
Yes, there, we at the back, and then you here. I wanted to ask you about the nervous system and neuron system. You said it is very difficult to replace it or if it gets hurt or something. I want to ask you how much research has been done about it, and like, if we want to make an artificial intelligence, so do we need to replicate just the brain, or how much part of this nervous system and neuron system play in our consciousness and all?
Okay. Oh my God. I mean, all right. Okay, let me break that question down. First question, which is how easy is it to replace neurons and how much do we know about that possibility? Difficult to replace neurons. Think about it like replacing a layer of skin, okay? This is doable. I burn this patch of skin, I can take donated skin, I can take skin from some other part of myself, I can put it back, I can replace skin, right? We're talking about local effects. Now think about a motor neuron sitting on this side of my brain controlling this movement. Where is that? That neuron sitting here. We're talking about almost a meter long projection down, half a meter long projection down that's driving this. So I might be able to put a neuron in here. How is it ever going to connect up back to the muscle that does this? So this is a much more complicated problem than locally replacing. So it's going to be difficult for long distance projections. But there might be overrides. For example, I could say, forget about this connection. Let me just drive it locally and start doing it here. What if I can electrically stimulate locally and drive it? And then you can do that. But your diversity of movement will be difficult. I might be able to do this, but I might not be able to play like, you know, the violin, because that's so much more complex than simply doing a simple movement. But that will happen. That's a matter of time. We've figured out ways by which you can electrically activate circuits locally, and you will be able to do this much for sure. You're not replacing the neuron, you're just saying, forget it, I don't worry about control, I'll locally drive it, okay? You've just lost the connection. Replacing neurons, you probably imagine starting off locally. It'll have to be neurons that don't have very long distance projections. The adult brain is hostile to new neurons growing and sending out projections. Nothing really grows actively in your nervous system in terms of neuron growth. Glia divide all the time. That's where brain tumors come from. They come from stem cells or glial cells. You don't have a neuronal tumor, which is actually neurons that have been created usually, right? So it's unlikely we're going to get to a point where we have the ability to, we can make mini brains. Mini brains are basically, they have some features of the brain in a dish, but it's not a nervous system. And it's certainly not a nervous system that is connected and able to orchestrate function. Far away from that. Consciousness, I can't even answer that question because we don't have, and you know, it's like I said somebody said War and Peace, Tolstoy or whatever. It's like writing a novel when you've barely deciphered the alphabet. So that's one of the most complex questions. So we don't even really have a good handle on it. As far as artificial intelligence is concerned, it's learning how to train a network to use the similar properties that the nervous system uses and to learn and have weighted changes that allow you to actually incorporate information and modulate a response.
Ma'am, as per Indian knowledge, we have three subdivisions of nervous system. I don't know nervous system, the right correct equivalent of nadi. So we have pila summa. So they are supposed to trigger different kind of emotions. So is serotonin is somewhere related to that, or is there any research on this?
This is a bouncer. I can't even answer it because I don't even know what the equivalent would be. This is language and vocabulary that is in two different planes, right? That is not to say that traditional knowledge doesn't often have empirical evidence which is profound, because it's just observational in many, many cases. Everything that we've used in modern medicine in many cases is plant-derived, indigenous knowledge dependent. So I don't know what the equivalent of that would be. So I don't know. I mean, I know there are people who've sort of looked at genomes and genomic associations with Prakriti, which is again something that comes from figuring out what your original predispositions are. But with serotonin, I have no answer. This is such a hand-waving answer. That's the worst answer on the planet, sorry. Yeah.
How exactly does serotonin protect the neurons? And secondly, what kind of a role does serotonin play with regards to the glia and the astrocytes?
Ah, very good. I'm back to terra firma. I can handle this question. Thank you. How does serotonin protect neurons? It looks like serotonin protects neurons in this particular case against oxidant or excitotoxic damage by upregulating superoxide dismutase and catalase. So really dramatically upregulating them, scavenging free radicals. So you get a profound decline in ROS. And so those might be two of the major ways via which you're just cleaning up the territory. So it's almost as though if you produce so many free radicals, we just bring them down dramatically. So it's not as though at some dose you will not die. So you could have, for example, even if you put bleach, put H2O2, eventually all neurons die. At high enough concentrations, whether you have serotonin on board or not, you will die. The neurons will die, right? But it protects over a much longer range before you hit that point. So that's one of the known mechanisms. There might be way more. We've just uncovered a little bit. Yeah. What was the second question?
What kind of a role does serotonin play
with glia? We don't know. We have to ask. So glia, we really don't know. I mean, it's possible it has a role. We've certainly talked about it. A lot of our in vitro data was done in neurons without glia around. We also did experiments straight in the brain where glia are there. Glia are the other major support cells within, in fact, the main support cells in the brain. More glia in your brain than there are neurons. We don't know. We don't know the effects on glia. We don't know the effects on the gut. So we don't know many, many effects.
Other neurotransmitters that can, like GABA and all that can end up protecting the neurons, or just serotonin?
Yeah, so we looked at activity, excitatory neurotransmitters. So is it only serotonin that has this neuroprotective effect? Melatonin has a neuroprotective effect. N-acetyl serotonin has a protective effect. Dopamine has been shown to have a suggested protective effect, but not in the population of neurons we've looked at in the reward pathway. It doesn't in the neurons we've looked at. Norepinephrine doesn't have an effect. Activity doesn't have an effect. So I think it will depend on which population of neurons you're looking at. Some neurons will be protected by a certain cocktail. Another set of neurons will be protected by another cocktail. That's what I think we're going to, but no, it doesn't appear to be every neurotransmitter does.
Vidita, thanks. Beautiful talk as always. The question is, with evening depression, which is non-clinical in nature. So, though serotonin level always comes down, but there are a large variety of individuals who report that as soon as sunset, and then they feel depressed. So, I mean, how does it happen, and how can we resolve that? I mean, as a general information that this, because this happens to a large, they never reports that exists.
Yeah. So the question is, what is the role of serotonin in the sort of sadness/blue state that happens as twilight is around? In some ways, the question fundamentally becomes: is sadness actually to some extent protective? As a species, we have such an aversion to a certain spectrum of emotions. We always say, be happy 24/7. Being sad is unacceptable, you cannot have the blues, and yet profound beauty has come from those moments of sadness, right? So to eliminate sadness, melancholiness, quietness, solitude, all of that would take away many, many things from the human experience. So I don't think one has to have this desire to instantaneously look at it clinically. I think it's the human condition, that there is going to be the entire spectrum of emotions, and some sadness is not a bad thing. It's a part of the human experience, right? I just think that when it gets into zones where then it crosses over into what do we define as healthy function? Healthy function cannot be like 24/7 happiness. That is just not sustainable. It's not even in the spectrum of normal. We run a risk if we start defining it so narrowly. So I would say, there was reasons why they have the ragas that are sung in the morning with sunrise, and what you have with sunset, and what you see with twilight. So I wouldn't worry so much about it unless it got into zones of pathology, where the person moves into a zone where they're pathologically finding themselves incapable of doing other normal functions. You could be sad and still be perfectly functioning. What was the question? I'm sorry, I didn't. Okay. I like that question. Cute. Thank you. What's the difference between serotonin and dopamine? They are both monoamine neurotransmitters. Serotonin is made from L-tryptophan. Dopamine is made from tyrosine. Yeah? So tyrosine gets modulated, and then you get further down. So it's essentially a different synthetic pathway that produces dopamine and produces serotonin, produced by different parts of the brain, different kinds of neurons. Dopamine is essential for our ability to do a lot of movement. Dopamine is essentially required for our feeling of reward and pleasure. Right? So they subserve different kinds of function. Structurally, they're very similar in that they're small molecules. They're very different receptors, different enzymes that produce them. But they're neurotransmitters in the brain. So is norepinephrine.
Is serotonin always produced from tryptophan in the brain and not from the enteric system? Is there any transfer from the enteric system to the brain?
Yeah, so this is an interesting question. The question is all the serotonin in the brain only locally produced, or do you get serotonin from any other site? There is a fair bit of an ascending nervous system, which is your entire gut receives a lot of neuronal input, and there is neuronal output. Okay? You think about your universe as all that this comes in contact with. You basically are a donut. I don't know if you realize that. You have a hole here and at the other end, which I'm not going to tell you anything about, but you're basically a donut, right? You're essentially a donut, and that donut is We only talk about the experience that is created on this part of our skin. There's huge epithelium that goes all the way, and that is also our experience. So if you think about it, the universe is outside and going through the hole. So there's constant interaction. So that's the other place where the sensory systems have to take tons of information from. So as much as you're talking about bacteria all over there's the gut microbiome, somebody said, your entire gut is also exposed constantly to the external universe, in a sense. Things are going through, right, constantly. So there's a lot of ascending input. Where the serotonin goes through all the way up, a little unlikely. Transport happens locally. There's a lot of serotonin in your gut. There's a lot of ascending input from your vagal nerve, which can carry all the way up to your midbrain, and from midbrain up. So it certainly can modulate the brain, quite dramatic. But I'm going to leave it as we don't fully know. For the following reason, that we read a paper last week where prions, I don't know if you know about prions, yeah, so these are proteins that are not folded properly. Somebody took a prion protein that was not folded properly and fed it to a rat, and in that animal, turns out that it enters the vagus, goes up from the vagus all the way into the brain, gets directed to the dopamine producing neurons that control movement, and produces Parkinsonian symptoms. So this is wild. So then how do you know it's real? They cut off the vagus and you don't get anything. So they've just cut off the vagus. So prion crossing over all the way in, and obviously regulating your own endogenous prions. So if you take a mouse that doesn't have prion protein, you don't get these, because you have an external prion, but it cannot modulate your own prion. So sometimes when we say a categorical statement, no way, we don't necessarily know about whether it has been really, really looked at. But in terms of eventual effects on the brain, huge. Vagus nervous system, vagal nerve.
How can you detect the level of serotonin in your body?
So people usually do it with high performance liquid chromatography. Detecting levels of serotonin in the brain is done, it's a small molecule, you can detect it using chromatography. It can be administered, but most of it will be finished off in your gut if it is administered that way. It's not going to cross into the nervous system through the blood-brain barrier. You need the precursor to cross, so that's why the L-tryptophan. So you will have local effects of serotonin.
Wait, was it done with the person behind you, but it's okay, go ahead.
So I want to ask about, when you spoke about the leaves being wounded and people serotonin and heals. So how does that work with humans? Like when we're wounded, does serotonin have a role in that? And is that why people who are often depressed or suicidal hurt themselves?
Oops. Okay, let's finish the first question. That one's easily handleable. Platelet aggregation. So wound, you cut yourself, you have to coagulate, you have to close, you have to heal. Platelet aggregation is dramatically regulated by serotonin. Okay, so that's a direct wound healing related function. Cutting yourself and serotonin is now going to say that you have to be in a mood state that allows you to go to self-harm. Mood states that take you to self-harm certainly happen in a subset of individuals who are clinically depressed, and self-harm is something that could be cutting, it could also be suicidal ideation or attempting suicide. Does serotonin contribute to that? Certainly, but is it the only thing that does it? No, there's multiple circuits involved there. So I wouldn't link those two necessarily. But there's no question there's a role for serotonin in self-harm. The first one is easy to answer, it's platelet aggregation.
I have a question. It's a bit off-base, but I wanted to know if we don't remember dreams, but we know the feeling. I mean, how is that? Just wanted your input.
Yeah, okay, so that's my newest master student right there. Googly of a question. Why do you not, so the question is, you may not remember your dream, but you may remember how you felt with your dream, okay? I don't know if, that's a tough one. Part of the problem is a lot of our studies in dreams in rats do not allow us to ask about the subjective experience of what did you dream about? A problem, right? I can ask you, etc., but that's difficult to then study. But there's very elegant work from Matt Wilson's lab, which I'll tell you about, which I think was one of the most exciting papers. What they did is they were recording from the hippocampus. The hippocampus is a structure which has cells called place cells. So if I come to Prithvi, I've come to Prithvi multiple times before, I will have place cells that remember this place. I know where the cafe is. I know where I have to go in Juhu. So there will be place cells that respond to this territory. There are place cells that probably even respond to this stage, because I've stood here and given talks before, right? And if I've done it enough number of times, those place cells become stable for this environment. Every time I enter this, the same set of place cells will fire in a particular order and sequence. You can do this with rats or mice. You can put them in a maze. And when they're in the maze, as they go through the maze, place cells are creating context of the location, and you can record from the hippocampus and see the firing of these place cells in a particular order. So let's say they go A, B, C, D, E, F. That's the order in which the place cells fire. I'm just giving a random sequence, okay? Now this sequence, the animal is walking through the maze, these neurons are firing. It turns direction, it will fire in a different order, right? But these place cells fire and create a map. Now that animal comes back to that maze every day. It becomes a stable ensemble that fires in a particular order. You have electrodes stuck in the hippocampus, you're recording anyway. You let the animals go to sleep. In non-REM sleep, nothing happens. Those things are firing, but nothing is in any order, nothing is in any sleep. REM sleep, which is the state in which we dream. A, B, C, D, E, F. Replay. So they recorded this. So Matt, this is crazy, right? So this is the, you can't ask the mouse, are you dreaming of the maze? But the brain is telling you that you're replaying the exact same ensemble of neurons that played out when you were in that maze while you are sleeping, right? So you have this non-REM state in which you replay. You replay it, speed it up so fast that the animal cannot physically run through the maze that fast. So it's a very fast A, B, C, D, F, G. It can also go A, wait, long time, B. So it's like it's actually playing it in fast forward and slow motion and fast forward, but in that sequence. Now you stop and you wake up the mouse every time it enters REM. So you let it go through non-REM sleep, wake it up. Let it go to non-REM, wake it up. It cannot remember the maze. And you don't have a stable network. So despite going into the maze every single day, if it has not had REM sleep, it cannot learn and establish a stable ensemble. This is the closest proof we have. In humans, there's a lot of data where you've taken individuals, prevented REM sleep, shown that a lot of word association, learning, etc. goes. So you can teach individual tasks and they just can't remember, they've not gone through proper REM sleep, right? So there's a lot of human data as well. But in rodents, this is probably the strongest data that shows you how the network responds during the emotional element of that state, which there could be because there are nightmares and there are very pleasant dreams. We don't have a good readout of that yet.
Okay.
But fear memories are always strong.
We don't have much time. Girl in pink, guy with a hat.
With pink and that. Okay, I will keep short answers.
Go ahead.
How does serotonin act as an antidepressant? Okay, wow, it's a killer question. I can give you the blurb that the pharma industry will tell you, okay? The blurb that the pharma industry will tell you, serotonin, or even a psychiatrist may tell you, a good psychiatrist should not, but a psychiatrist will tell you, it elevates serotonin levels, you're going to have higher levels of serotonin, and so you're going to feel better, and it's going to improve your mood. The problem is it's not as simple an answer. In an acute phase of exposure to a drug which is an antidepressant elevating serotonin levels, acutely you actually get an increase in anxiety, which is the first response. You actually have an acute elevation of anxiety. Like I was telling him, it's a hammer. You're hoping with the hammer you will hit the right circuit. It clearly hits circuits that control despair, that control the feelings of despair, and it does that, but it also hits circuits that regulate many, many other things. They don't work immediately. They take a good 3 to 6 weeks to work. That is if they work. They work in 60% of rodents, patients, 40% will not respond to anything out there. That is a treatment-resistant group that doesn't respond to the currently available, easily available medication. So I don't have a clean answer for you that says this is the precise circuit. There are certainly, so for example, we know the medial prefrontal cortex to raphe circuit will regulate the feeling of despair and hopelessness, which is a major symptom of clinical depression. But when does it work on that circuit? It will also work on the amygdala, which will produce fear. So you will have simultaneous effects. Eventually, you take it long enough, some effects dominate over the others. Compliance is poor with drugs because you imagine if you have a headache and somebody gives you a pill and says, maybe it will work after 3 or 6 weeks. You're not going to take it, right? So this is the biggest problem. And also, you feel sorry for the psychiatrist. You don't have a guaranteed prediction which drug is going to work in which patient. This is a real challenge. It's a challenge for the psychiatrist. There's no question they do work, but who will they work on? How effectively they will work, and which combination will work and which drug will work? It's a bit of it's guesswork, right? Real guesswork. There, the pharma industry is going to take a gun and shoot me. That's it.
How much time does it take for serotonin replenishment, and does it degrade as life passes by? And which would be the most optimal time or the best time in your life that your serotonin replenishes?
Okay, so turnover rates of serotonin, how quickly do they turn over? Do we know 12, 14 hours? What is the turnover time, metabolism wise? Yeah, half-life is, yeah, it's like in the hours range. So you turn over so it's metabolized by mitochondrial enzymes like the monoamine oxidase, which break it down to downstream products. People have measured this, but in the brain, at any live synapse, this has not been, you don't really know the exact half-life, in the hours range, within 8 to 10 or 12 hours. Across the lifespan, it's highest in the earlier windows of life, so that's postnatal, young adolescence, and middle-aged and onwards, it goes into decline. So but that's going to be the broad feeling. It will be variable within each individual. So that across that, overall, the aged population will have the lowest levels. Serotonin in the young and developing nervous system has huge effects.
Can TMS actually give a nice stimuli to serotonin replenishment?
So TMS is usually not done in circuits that release serotonin. TMS will be applied on circuits that receive serotonin. So you could, with TMS, so TMS is transcranial magnetic stimulation. It's a treatment that is used for depression where locally you apply magnetic stimulation to modulate local activity. So using that, you could kickstart, for example, if it was done in areas that hit the prefrontal cortex and MPFC, you could reactivate a circuit to start responding more effectively. Unlikely to directly modulate.
Yeah, sorry. Okay, wait. End of the question.
We'll talk later.
Giving you a chance. It's already past 1 o'clock. We're going to throw a quick question if you have one.
It happens that we have experienced this scene somewhere, but we have not come here before.
Deja vu? Yeah. So, okay. I'll quickly do it. Yeah. So what's the underlying neurobiology of deja vu? Okay. Again, we can't ask a rat, are you having a feeling of deja vu? So we are now inferring. Okay. Memories are often thought to be encoded by neuronal ensembles. So let's say my place circuit here is A, B, C, D, E, F, G. Okay, I'm imagining this scenario. It's a population, it's not going to be 5 neurons, but it's going to be a network of neurons that have encoded my memory of the space. For whatever reason, I activate A, C, D, E in a new location. There could be some partial cue that drives it, enough to get partially the network up. So I have a partial network activation. When I have a partial network activation, I could quickly slip into activating the rest of the network because it's prone to be activated as a collective. So I can have a partial element of it, but it produces a full-fledged feeling of, I remember this place. Okay? It's only because something ticked off half of the component enough to give you the full. That's what we think drives deja vu. Of course, this is conjecture, but that's likely the explanation.
All right, you said it was okay to be sad sometimes.
Yes.
Okay, so once you couldn't have your questions answered, feel sad. It's okay to be sad for a while. You can email us, put the questions on Facebook, etc. on the event page. We will try and get them answered. Thanks again for coming. Thanks. you live audience for watching. And just remember the next Chai and Why, 2 weeks from now at Ruparel College, is all the interesting things you can see from a local train window. So science from a Mumbai local train. That's Chai and Why 2 weeks from now. If you are not on our list, I see lots of new faces. Follow at Chai and Why on Twitter or Facebook, or send us an email, outreach@TIFR. We will add you to our email list. Okay?